Assalamu alaikum everyone. This is lecture 19 on Control System Engineering 1. We are discussing chapter 7, Steady State Errors. In the last class, we have derived the formula for the steady state error. That is E infinity equal to, in the Laplace domain, limit s tends to 0, S ES. Okay, so in terms, we are generally interested in terms of G of S. So the formula was something like this, limit S tends to 0, S R of S divided by 1 plus G of S. Okay, so then then we have derived for different type of inputs, what are the changes that we have. So E state, E infinity for the step signal, we derived a E step infinity equal to 1 by 1 plus limit S tends to 0, G of S. Okay, so for this one, we have seen two different scenarios for how many poles at the origin. Based on that, we have find different values of steady state error. So number of the pole at the origin and what happens to the steady state error in step infinity. Okay, so far what you can recall is if n equal to 0, then we are actually finding some finite constant value. And if n was 1 or higher, in that case, we have found that the value is basically 0. So two possibility was there. Either you have 0 steady state error, or you have some finite value based on the value of n. N is the number of the pole at the origin of your forward path transfer function, also known as system type. Okay, so then for ramp input, we also calculated the steady state error, and we found the formula something like this: 1 by limit s tends to 0, S G of S. And also we figure out the relationship with n, number of the pole at the origin, with your E ramp infinity. That was if n was 0, then we figure out that the steady state error was infinity, which is evident from here because this denominator will be 0, so 1 by 0 is infinity. And then if n equal to 1, then S is getting cancelled out. So we are getting some finite constant value. And if n equal to 2 or higher, in that case, we find 0 steady state error. So this is the condition for how many poles we have at the origin. Based on that, these are the three values. For this step, there is only two possible values. Last time, I think we have used graphically. We tried to explain it graphically. Now, this time, it is also mathematically we prove this scenario. And the final one, E infinity for the parabolic input. Okay, so we had a formula something like this: 1 by limit s tends to 0, s squared g of s. And similarly, n, and based on the value of the n, and that is system type, we have seen that for 0 and 1, we have an infinite steady state error. And if it is 2, then s squared getting cancelled out. So we are getting some finite value, and n value is 3 or higher. In that case, we are going to get 0 steady state value. So one thing we have to consider is that there is these limiting factors. These are important to find out the steady state error. So this is one thing, as well as this parameter uh, pole at the origin is also one of the factors that determines the value of the steady state error. So for this step, there is two possibility for the ramp and the parabola. There is three possibility, either infinite steady state error or some finite constant value or zero steady state error. Now, what formula we have derived based on that, let us solve one mathematical problem which was supposed to be the starting of this class. So example 7.2. So test inputs that are provided to us, test inputs for all of them which we have to figure out. So the test inputs is 5 UT. So step input, but the magnitude of the step is 5. Then 5 TUT, that is ramp, and 5 T square UT, that is parabol. Okay, so this is what we have to figure out. For these test inputs, we are giving a negative unity feedback system, very simple one. 120 into s plus 2 divided by s plus 3 s plus 4. Okay, so this is the scenario. This is our R of S reference. This is our C of S. Okay, now for this different test input, we have to find out the steady state error for this system. Now, we already know this is, we can also calculate what is the system type for this one. So there is no pole at the origin. So basically n equal to 0. So this is actually type 0 system. So this we already know. So for the type 0 system, we know that the input signal should be applied is basically the step input. So other two will give us 0 because if the pole at the actually will give us infinite steady state error. So let us now see whether whatever we are trying to figure out that is true or not. Okay. So even though you know that the value we are going to get is only for this one and these two will give us infinite steady state error even without solving based on the values of the n that we have calculated as seen in the last class. Okay, so first thing first, let's start with step one. So it is always better to go with your original formula. That makes things a bit easier. So limit s tends to 0. Also, if you want, you can also write e step infinity. So limit s r of s divided by 1 plus g of s. So now r of s is basically 5 ut. So in the Laplace domain, 5 1 by s. So basically s into 5 by s. Okay, and 1 plus the g of s that we have, that is 120 s plus 2 divided by s plus 3 s plus 4. And don't forget the limit, it is always there. So now this s and s is getting cancelled out. What is left is basically 5 divided by 1 plus. Limit is only applicable where the s terms are available. So we can directly put it here, and s plus 2 and s plus 3 into s plus 4. As you know, if the s is been replaced by 0, then what will be left here is only the constant terms. So basically 5 by 1 plus, that is 120 into 2 divided by 3 into 4. So basically 120 divided by 12, 10 into 2 is 20. So what we are going to get is 5 by 21. So this is our steady state error for the step input. Now what will be the case for the ramp and the parabolic one? So E infinity for the ramp is E ramp infinity is limit s tends to 0. You can start with the original formula because of the fact that we are given 5 ut, 5t ut. So how to replace them, that will be easier if you start with the original formula. So 5t is basically 5 is a constant and put is our concern. The corresponding transform into the Laplace domain, 5 will be remaining as it is. T is basically factorial 1 divided by s plus 1 plus 1, s to the power 1 plus 1. So basically it will be remaining just 1 by s square. Okay, so just those who forget the rules, t to the power n ut is basically factorial n divided by s n plus 1. Okay, so now what we have is 5 by s square. Then you have 1 plus g, sorry, limit s tends to 0 g of s. So now one s is getting cancelled out. So another s will be going to the denominator, and then we can apply the limit. So basically 5 will be there. Limit s tends to 0. S plus s, sorry, accidentally the limit is given here, but the limit is outside. So this is the scenario now. Now if you put the limit, then 5, then actually limit s tends to 0, s g of s. So as you can see, this is a type 0 system g of s. So basically s will be dominant. So this parameter will be basically 5 by s equal to 0. So what we are going to get is infinite steady state. So similarly, we can say simply that it will be also infinity for parabolic input. But what are the changes in the input? This is important. So let's see how we can find that one. E parabolic, even though we know the result, but how to put the input, that is what we are interested to see. So limit s tends to 0, s r of s. So r of s is now is basically rt is 5t square ut. So now if you take it in the Laplace domain, 5 will be remaining as it is. Now factorial 2 divided by s 2 plus 1. So what we are going to get is 5 into 2, that is 10, divided by s cube. So this is why sometimes this parameter is not 5 now, rather it is 10. So that is why I tried to, even though you know the result will be actually infinite steady state error, but still what will be the value of the input? That is why I am doing it. Now what we have is 1 plus g of s. Now as one of the s has been cancelled, so what we'll have is limit s tends to 0, s square plus s square g of s. 10 is there. Now if you put the limit, then this s will be dominant. So basically 10 by 0 will be there and infinite. Okay, so this is where they think is a bit critical. So with a higher order of n, higher values of n, we have to be careful about that factorial n. Okay, so rest of the problem is basically very simple. Now go for another example, example 7.3. So example 7.3 actually gives us another forward path transfer function, same 5 ut, 5t ut, and 5 t square ut is applied. So now just instead of drawing those diagram, rather let me apply it directly. So g of s is provided forward path gain, that is 100 into s plus 2, s plus 6 divided by s into s plus 3 and s plus 4. Okay, so now for this system, whether which one we should go for. Now we know that this is s to the power 1 is there, so this is a type 1 system. Type 1 system, and only if there is in the input you have a s square, only then, because in the formula you have rs, s into rs, and also in the g of s you have 1 s there. So if this parameter is 1 by s square, then this will be cancelling each other. Eventually we'll get a finite value. So we know that only for the ramp input we're going to get some finite constant value. But if it is a step, since the number of the type is higher than uh, the input or at the origin, so basically it will give you 0. And if you apply the parabolic, and then your error will be infinite. So these are the two things we already know. So there is no point of applying those two here. Rather, based on the system type, actually we should go for only one calculation. Unless otherwise the problem specifically ask you to figure out the steady state for error for all three inputs. I think it will be wiser if they don't ask in that way. Then you go for only the one that matters. Okay, so I'm not doing the other two because I know the result. So I'm just going for the one that matters, that is E infinity equal to E RAM infinity, that is you can apply directly or you can use a fundamental formula, so it's up to you. So 1 by limit s tends to 0, so s g of s. Now problem here is you have to be careful about this parameter here. Okay, so if you're directly applying, now we're not sure what should be this value, isn't it? So this value here has to be 5 because our input is 5 TUT. Okay, so it will not be 1. So that is why it's always better to come with the original formula. Then the possibility of error will be reduced. So what we are going to get is 5 by limit s tends to 0 s g of s, that is s into 100 into s plus 2 s plus 6 divided by s into s plus 3 s plus 4. So basically s is getting cancelled out, then this 12 is getting cancelled out, so 100 is remaining. So basically 5 by 100 is your result. So 1 by 20 is your steady state error. So this is your final value of the steady state error for the ramp. And for the other two, step and the parabolic, we already know the values. For the step, it will be 0, and for the parabolic, it will be infinity. So basically, system type has a lot to contribute for steady state analysis. So these three parameters that we have figured out already. So basically, E step equal to 1 by 1 plus limit s tends to 0. Sorry, g of s. Okay, so then for the ramp, 1 by limit s tends to 0 s g of s, as well as for the parabolic one, 1 by limit s tends to 0 s squared g of s. So this uh, three parameter, this limiting parameters in the denominator is actually contributing to your steady state error. So, and determining the steady state error. So these three parameters, these limiting parameters are known as static error constant. Static error constants. Okay, so specifically this one is known as KP, position constant. Okay, position constant. And the value we already know, limit s tends to 0 g of s. And this particular value is known as kv, related to velocity. So we call it velocity constant. And this is limit s tends to 0 s g of s. And similarly, this parameter is known as ka, acceleration constant. And this is what is limit s tends to 0 s squared g of s. Okay, so these are the definitions. Just like in case of your transient behavior, what was the performance of your uh, settling time, rise time, zeta, all this thing. Similarly, in case of your steady state analysis, these are the factors that actually determines your steady state error values. Now, what are the factors that actually contributes to our steady state error? So far, whatever we have understood is, first of all, these three parameter, that is static error constant. So basically, Kp, either one of them, Kp, Kv, or Ka. In addition with that, what is the form of g of s? That means we are actually interested about the type of g of s. So basically, we can also write in bracket type of g of s. Okay, so based on these two parameters, so what are the results that we are going, that are having three type as well? One is zero steady state error. One we're getting is some finite constant value. And then we have infinite value. So these are the three possibilities based on those things. And also one of the thing I think you already have noticed that all these limits of the steady state error is actually appearing in the denominator of the equation. So basically we can say that we can also keep a note that steady state error is actually inversely proportional to steady state static error constant. So this is actually static error constants, that is Kp, Kv, Ka. Okay, so let us go with another example, example 7.4. Example 7.4. So basically three different transfer function is given, and for those three transfer function, we have to figure out all three, we have to apply all three test input. But whatever we know so far is it's worthless to apply other two because we already know the result. So first transfer function that we have is something like this: 500 into s plus 2 into s plus 5 divided by s plus 8, s plus 10, and s plus 12. So this is the first one. The second one is 500 into s plus 2, s plus 5, s plus 6 divided by s plus 8, s plus 10, s plus 12. The change is this one, so we have s here. And the third one is g of s equal to, the parameter is actually increased, so 500 into s plus 2, s plus 5, s plus 6, and s plus 7. S plus 7. Then we have s square. The rest of the parameter is same, s plus 8, s plus 10, s plus 12. Okay, so what are the changes? Basically, this is type 0. This is type 1. And this is type 2. So what we know from our previous discussion is the suitable signal to have some finite constant value is step for this one. For this one is ramp. And for this one is parabolic. Okay, so based on that, what we can say that the performance parameter, static error constant for the first one has to be Kp. For this one, it has to be Kv, and for this one, it has to be Ka. So what is the value of Kp? The value of the Kp is limit s tends to 0, g of s. So basically all the s will be replaced by 0. So 500 into 2 into 5 divided by 8 into 10 into 12. The magnitude is around 5.208. So if you are interested about the error, steady state error or steady state error is basically 1 by 1 plus Kp, that is 1 by 1 plus 5.208, which is approximately 0.161. Okay, so this is the first one. And the second one, we have to find out the Kv. So the value of the Kv is limit s tends to 0, s g of s. So basically this s will be cancelled with this s, and rest of the parameter just replace the value of s by 0. So 500 into 2 into 5 into 6 divided by 8 into 10 into 12. Now this gives us a value 31.25, and K, so E infinity or E ramp infinity is basically 1 by 31.25 is 0.032. Similarly, if we go for the Ka, so K is limit s tends to 0, s square g of s. So now s square and s square is getting cancelled out. What is left is 500 into 2 into 5 into 6 into 7 divided by 8 into 10 into 12. And this will give us around 875. So your E infinity or E parabolic infinity is 1 by that factor, that is around 1.14 into 10 to the power minus 3. So this is your steady state error. So far, whatever we have seen, the importance of this system type the dependence of your system type on the steady state error is crucial. So if we have a generalized equation, g of s equal to say s plus z1, s plus z2 goes on. Similarly, s to the power n into s plus p1, s plus p2 goes on. So then this one is what we define as n equal to system type. System type. Now, based on the unity feedback system and whatever we have discussed so far, we can actually conclude with a table like this, which is actually your table 7.2. Okay. So now let's take that one into account. Okay, so table 7.2. I believe this is visible. Now we already derived most of it. So for step input, this is our formula for steady state error. And for ramp input, this is a formula. For parabolic input, this is the formula. So for the type 0, so g of s doesn't have any pole, so only have s plus z1, s plus z2, s plus p1, s plus p2 goes on. So basically for type 0, since we are just taking the limit of g of s, so it will give you a constant value. For other two, since we have a higher order of terms, s will be multiplied with, then basically we'll have zero steady state. Similarly, for the type 1, as you can see, for the Kp value will be infinity, and because of which your steady state will be 0. Then you have some finite value, and then for higher values of input, we are going to get infinite steady state. Similarly, for the type 2, the first two parameter will give you 0 steady state error, and third one will give you a constant value. And if the value of the input is having higher order of s, say s s to the power 3 or s to the power 4 goes on, in that case, that will give us infinite steady state error as well. But we in general, we are actually interested about these three input. So this is what we already have discussed. Now, what is the steady state error specification? As I have already said you that steady state error specifications. Okay, so just like the values of percentage overshoot, TP, peak time, settling time, or the damping ratio that actually defines the transient behavior. Similarly, here KV, KA, or KT, they're actually defining the value of your steady state error behavior. So say arbitrarily we have a value given KV equal to 1000. Okay, so what does actually it mean? And the meaning of this is, first of all, one thing we have said in the last class is that the steady state error only applicable for a stable system. So since they have already figured out KV, the first interpretation has to be the system is stable. System is stable. And the second one is uh, since they are dealing with KV, so we know that KV is actually related with type 1. So KV is gives us a system type. So the system type is 1. And thirdly, and since it is a finite value of KV is only possible for the from the ramp input. So we can also gauge the type of the input. So input is actually ramp. And finally, don't forget that It also helped us to find out the steady state error. So state error is 1 by kV. So this will give us 1 by 1000 is our steady state error. So all this information is actually can be obtained from your value of the steady state error specification. So similarly, one example is given, example 7.5. So in that particular case, what is provided is Kp value is given, example 7.5. Kp is given is 1000. So what are the information we can get? First of all, definitely it has to be stable. Secondly, Kp, that means the system type is zero. Zero system type is only giving a finite value. Thirdly, the input is definitely step. And fourthly, your steady state error, you can directly calculate 1 by 1 plus 1000, basically 1 by 1001. So this is your steady state error. Very simple idea. Now next is example 7.6. So this is a design problem, basically design problem. So how can we take advantage of this error calculation to design our system? Okay. So we have a system something like this, RS. So negative unity feedback system, K by S plus 5 divided by S plus 6, S plus 7, and S plus 8. Very simple problem. Now what it says is, this is our error, this is a sign. So they're asking you to find out the value of the K so that there is 10% error, 10% error in the steady state. So this is simple as this. So they're asking you to find out what should be the value of the K. So to basically design or figure out the value of the K so that the steady state error is 10%. Now, first thing we have to find out is what is the system type. So this is example 7.6. So first thing is the system type. So one pole at the origin. So this is a type 1 system. Okay, so this gives us the information that it is the steady state error is related with the parameter static constant. Static error constant should be kV, and also we should have ramp input. Okay, so by default this is what we can get. Now, so what is our error? Error is basically 1 by kV. Okay, so error is actually 10%. Okay, so that is 0.1. So kV, value of the kV we can calculate. So the value of the kV is basically has to be 10. Okay, but we don't have to. Now, what is the value of kV? According to the formula kV is limit s tends to 0 s g of s. So from this one we can find out that s g of s, this s is getting cancelled out. What is left is k times 5 divided by 6 into 7 into 8 equal to, it has to be 10. So from this one, you can easily see that the value of the K has to be 10 times 6 into 7 into 8 divided by 5. So basically 672 should be the value of the k. So we know that for the value of the k to be 672, we are going to get a steady state error of 10%. Okay, so sorry for the interruption. So now we already calculated the value of the k. So the value of the k 672 is gives a 10% error in this particular given system. But one thing we have to be always careful is whatever the system is for the value of the k, whether the system is stable or not. This is what we also have to test. So stability is needed to be tested. Okay, so it may happen that for this particular value of the K system is going to my system is bringing some polling to the right of them. So system may not be remain stable. Okay, so that is why it is always better whenever you're designing something, then also go with your stability analysis. Now, this is so far what we have seen is the steady state error for a particular system without any disturbance. So sometimes it may happen that in our system there is some disturbance input is there in some junction, maybe some electrical noise is being produced, step type or ramp type, parabolic type. There is or random type noise may be there or disturbance signal may be there. So based on those whenever these disturbances are present in any system, actually how to find out the steady state error for that particular system. So let us start with that one. So steady state error for disturbances. Okay, say that it can be the noise can be in any junction of your control system. Just arbitrarily, we're just taking a particular scenario. So, say this is our the forward path transfer function G1S. In general, this is actually the controller. Then we have a junction that actually introduces the disturbance D of S. Okay, and then we have our actual plant that is G2S, and this is our output, and also we have unity feedback system. Okay, so the signs are important. So plus, minus, RS, CS. So we're assuming that additive noise is or disturbance is there. So now this is the scenario, and this is our error, yes. So let us see how can we derive the formula for the disturbances. As I already said, it can be in any location. Just we are assuming in this junction we have the error. Now let us derive the formula. So again, our error is formula is simple. The steady state error is limit s tends to 0 as E of s. So basically, for this particular case, we have to find out what will be the value of E of s so that we can put it here and find out what will be the error formula for this particular case. So formula for the error is same as before, always same, that is Rs minus Cs. Now in this case, what is Cs? Cs is actually E times G1 plus ds is basically into then G2 is actually our Cs. So we can replace that one here, Rs minus Uh, so that signal that is coming here is ES into G1S. So these two are added, then multiplied with G2. So basically what we can write here is G2S into G1S ES plus DS. Okay, so what we have here is RS minus G1S G2S ES plus G2S DS. So we can be taken to the other side. So we have ES equal to 1 plus G1S G2S equal to RS RS plus, sorry, there has to be a negative sign because the whole term is negative. So if we multiply, so this one has to be negative. So okay, so minus G2S ds. So now if you simplify a bit more, then your arrow is becoming ES equal to RS by 1 plus G1S G2S, which is almost as before what we had, minus G2S ds by 1 plus G1S G2S. Okay, so now finally we can apply the limit. So error, steady state error infinity should be equal to limit s tends to 0 s e of s. So basically what we have is limit s tends to 0 s r of s 1 plus g1s g2s minus limit s tends to 0 s g2s ds by 1 plus g1s g2s. Okay, so now as you can see, this particular one is because of the input RS, and this particular one is because of the input D of S. So we can say that this particular one is because of ER infinity, steady state error, due to the input R of S, and minus or you can generalize, so plus e to the power E because of D. Okay, so what you can find here is ER infinity is basically limit s tends to 0 s r of s 1 plus g1s g2s. So if noise was not present, then G1 and G2 can be multiplied together to have with G1, so which is same as before. But the new thing or the contribution of the noise or the disturbance that is becoming is ED infinity, that is a limit s tends to 0 s G2s D of s by 1 plus G1s G2s. Okay, so one thing we have missed, what is that? The negative sign. So always be careful. We are engineers, so a sign is very, very important. It can reverse the whole scenario. So now for simplicity, let's say that let D of S is a step change, a disturbance that is step disturbance. So in that case, what should be the value of EDS? Is basically minus limit s tends to 0 s g2s into 1 by s, then 1 plus g1s g2s. Okay, so then we have s getting cancelled out, and also we can divide this numerator by this parameter G2S. So what will be left is 1 by G2S, 1 by G2S plus G1S. Now if you insert the limit here, so E t infinity, infinity should be equal to something like this: 1 by limit s tends to 0, 1 by G2S plus limit s tends to 0, G1S. So since this ED is a contribution to the error, and because of the disturbance, actually we want to eliminate it. So, or at least minimize it. So what are the ways of minimizing the error contribution due to the disturbance? Is either we have to maximize this parameter. Okay, so either we have to maximize this parameter or we have to minimize this parameter so that this parameter is maximized. Eventually your error contribution due to the disturbance is lesser. So two ways. One, the limiting factor of G1 S has to be higher, or the limiting factor of 1 by G2S is higher. So G2 has to be lower or G1 has to be higher. So G2 has to be lower or G1 has to be higher. So is it understandable from the figure? So what they're saying is G1 has to be higher. So that means the contribution of this one has to be dominant, and the value of the G2 has to be lower. So because D is only multiplied by G2, so if the value of G2 is smaller, then the error contribution from the D or the disturbance input will be also lower. So from the diagram also, it is quite uh, intuitive to understand why G2, minimizing the G2 will be improving the steady state error because of the disturbance input. Okay, so this is the thing that we have learned from this one, how to derive the formula with the disturbance, as well as what actually happens, what are the ways of minimizing that disturbance. So now let us say and see how actually is it possible to adjust somehow in the system with the controller so that our contribution of this one is totally nullified. So is it possible or not? So this is, as I said, this is in general the controller, this is the plant. So what are the ways? For that one, let us apply the superposition. Only we consider this is our input we have, and this one is not present. So just assume that RS equal to temporarily, the RS is 0. So applying the superposition. So we can have actually DES is now the input. We are rearranging this block diagram. So this is our DS. Okay, then we have the plant in G2. Okay, so this is our error minus ES. And now our feedback is basically through the G1, the controller. Okay, so just we have rearranged the thing. We just make this output is our, like, the error is our output. And then we have, I use the feedback analysis and with RS equal to 0. So now what we can actually find out from this superposition block diagram is that somehow we have to uh, change or adjust the gain G1 so that these two parameters can nullify each other. Okay, so if DS is somehow equal to G1 ES, then actually the error contribution because of the D will be nullified. Okay, so this is what we can see. So the controller can be used to adjust in such a way that the contribution from this a disturbance signal can be nullified. Okay, so let us see one example related to that one, this one, and that is example 7.7. So we may have to use this formula. So example 7.7. So the block diagram is something like this. Okay, so this is the block diagram. This is your controller. This is plant. This is our disturbance input DS, and this is our step input, and this is our output. So what they are asking is to figure out the contribution of the error due to the disturbance input, and they want us to assume that DS is a step change 1 by S. Okay, so we already derived the formula here. So we take the help of this formula. So ED infinity equal to minus 1 by limit S tends to 0, 1 by G2S plus limit S tends to 0, G1S. So in our case, G2S is 1000, so we don't have to apply the limit. So we can directly put the value minus 1 by 1000. Okay. Sorry, it's not G2, it's G1. So put the value of G2. So limit S tends to 0, 1 by G2. G2 is basically 1 by S plus S into S plus 25. So S 1 by S into S plus 25 plus limit G1 is basically 1000. So now, as you can see, if you put the limit 1 by 0 is infinity. So this parameter is this parameter is becoming infinity. Now 1 by infinity is 0. So what we are going to get here is minus 1 by 0 plus 1000. So this is basically the contribution of our error. So minus 1 by 1000. Okay, so this is the disturbance input for the error contribution, steady state error contribution for the disturbance input. So far, whatever we have discussed in this class is basically, and up to this class is basically unity feedback system. So we have derived the formula for the unity feedback system, and we find out the static error constants and how a different input signal is related to these static error constants. Finally, we also have seen for the unity feedback system, if there is any disturbance, how to deal with the calculation or derivation of those disturbance, and what are the contribution of those disturbance to the steady state error analysis. And finally, lastly, what we also have seen for some formula for this one. So in the next class, what we are going to see is basically we'll start finding the formula for non-unity feedback system. Okay, so far everything was a unity feedback system. Okay, so in the next class we'll be actually discussing non-unity feedback system. feedback system, as well as if there is disturbances, then how to deal with those. And also, lastly, we'll be also discussing the sensitivity of the arrow. Okay, so these are the contents of the next class, inshallah. Okay, see you in the next class, inshallah.